Welcome, everybody.
Hello.
How's it going tonight, all you people out there of the world that are tuning into our stream, wherever you may be found?
And it's good. It's going good.
Dude, that's good. I'm glad you're
Uh,
doing good.
yeah, how are you doing, Kip?
Dude, I'm doing pretty good.
Nice.
Um,
Everything's up and running. It looks good on both sites so far.
yeah, we just have a lack of viewer problem, Jaden.
Right now, yeah.
Yeah, no one cares about Newton.
All right. I think a lot of people should care about that guy.
Dude, you think?
He, he kind of was important, I think. I don't know. What do you think?
Dude, I think he kind of was too. I think he's actually rated one of the most influential people of all time or something like that. Um, just in case
Pretty,
anyone
pretty wild.
pretty wild.
Should we start off by telling people what we're about, or should we just dive into it?
Dude, what are we about, Jaden?
Well, as our name says, we're aftermath tutoring. Uh, Aftermath, just saying like, hey, you come here, get some math homework done, math advice, also physics. But we thought aftermath slash physics wouldn't be as cool as just aftermath.
Doesn't flow as nice.
Yeah. So yeah, we're here to help. On Tuesdays we teach a lesson, kind of like a calculus physics course combined, and how physics use calculus and that sort of thing. On Thursdays we take any questions and we try and answer them. Um, yeah. So if you need homework help, come on Thursdays, ask all those questions in the chat or send it to the email. Um, Tuesdays, come here to learn, ask questions, have a good time. I don't know, did I cover
I think you did a good
it?
job, dude. I think you're killing it. Um, wait, so I can ask questions on Tuesdays? Sure, ask them away, but preferably about the lesson in which we're teaching. Um,
Yeah, that's what I kind of meant, but yeah.
yeah. Um. Anyways, Jaden, what do you think we're gonna go over tonight?
Well, as the screen says, and I hope everyone can read that's watching, Newton's laws of motion and more derivatives. Um, that's pretty cool stuff.
Yeah, it is. Okay, should we get going then, Jaden? Should we start off with some review from last week? For all you that don't
Sure.
remember what we did last week, we talked about some projectile motion, and we talked about some mins and maxes, and
What a
mainly
parabola
yeah,
is,
and vectors as well.
vectors. Yeah,
So Jaden's gonna
cool.
take us down memory lane with a first question.
Okay, so our first question we ask, uh, does this function give us a maximum or a minimum? Um, we're going to buy some time for you guys all to answer in the chat. You have two options, a 50% chance, or if you know it, 100% chance. Go for it. Maximum or a minimum. Remember, maximums are going to be like an N, and the minimum is going to be a U, right? So is this going to be an N or a U?
Yeah. Um, like this, Jaden. Boop. Doink. Or boop. Doink.
Yes.
Yeah.
Good stuff.
Which one is it going to be? Oh crap. Maximum. That's a question you asked. We're asking for an answer, not another question. You have to be sure about your answer.
Maximum?
Should we go ahead and give the answer away?
Yes, Kelsey, you are right. Even though you asked like a question maximum. Yes, but it is going to be a maximum. Uh, we know that it's going to be a maximum because of our. There she goes.
There we go.
Maximum 100%.
100%.
So we know that it's going to be a maximum because our coefficient of the term with the highest degree is a negative, and in this case, it's just quadratic. So we know there's only going to be one maximum or minimum, and in this case, it is a maximum because it is a negative coefficient.
Yeah, so it makes this frowny face instead of a smiley face. And so that makes it a maximum because there's a high point. Yes, you do win, Kelsey. Good job. Jen, should we move on to the second review question?
Yes.
What is a vector? So for all you despicable
Me fans out there.
Kelsey, why are my drawings interesting? Just remember that this is a PG rated live stream.
Oh. Come on, man. Okay. Yeah, so what is a vector? Kip, you want to answer this one, or should we give him a little minute for the chat?
Yeah, well, I'll just say, do you guys, there's a villain in Despicable Me, and his name is Vector because he is blank. He does blank and blank.
Direction and movement, but in different words.
Close,
Close. That is close.
but not necessarily movement.
Yeah,
Because
it starts with an M.
movement can be a vector, but it is going
Yes.
to be direction and magnitude. There we go. Nice. She got it before I finished saying it.
Nice.
Cool.
What a good student.
So what does that mean though, Jaden?
So without the direction, we'd be looking at something like speed, right? Or it's just a number. I'm going 30 miles an hour, right? We don't have a direction with that. But with the vector, we have both the direction and the magnitude. The magnitude is the number, all right, how fast we're going. We would be like 30 miles north, 30 miles per hour north, not 30. But anyways, I think you get the point.
I get the
right?
point.
We need both the direction and that speed.
Cool.
That's just an example of one of them. Okay.
Right. Is there another? Ooh, we just have our thought-provoking question now.
Yes.
So, the thought-provoking question is what is mass? And the only thing that I will say for all you guys out there that have no idea what mass is at all, right? It's the idea of the amount of substance or material essentially that exists. But what is that? And what does it mean? So, if you guys are getting confused by this question, then you are becoming a physicist and realizing that we don't have a better answer than you. So think about it. What does it mean for something to have mass? What is a mass?
Right.
And that will get us started on our lesson tonight.
But before that, don't we have something to show people?
Yeah, we do. I'm about to show them right now. Okay, guys. So, this is my most recent comic, I guess you could call it, that I'm coming up with. That will probably very soon be available on a t-shirt for you guys to buy if you want. And you'll seem super cool to all your friends because it's a math joke. Not only is it a math joke, it's a calculus joke. And since you've taken this class and you understand what a derivative is, you'll understand why it's so funny and you can impress all your friends. And they'll
Yeah,
think you're so smart. So there you
true.
go. But
That is true.
because get it, guys, get it, because it says it's not my fault that my instantaneous rate of change is zero because a constant's derivative is zero. Jen, did you get that?
Yeah, I got that.
You did, dude.
Yeah, dude, I love it. Um, I love how we have an X and a C
Yeah,
because C stands for constant.
yeah,
It's brilliant.
and the x, because its rate of change isn't zero.
Yeah, and it's getting angry at C because it thinks it's going to be late to the party
Yeah,
of functions, I'm sure.
yeah, I'm sure. And
It's going to
it's
be a functional party. Haha.
and the person they're going with, just no matter what, will never get there on time because they can't change.
Yeah, they can't change.
It's such a sad life.
Yes.
Okay.
All right.
All right. Should we keep moving on then? Because everyone thought
Yeah.
that joke was so funny.
Yeah. Uh,
Whoa, Jaden, there's some fancy writing on the screen here.
Whoa, Kip. Product rule for derivatives. What is a product, first of all?
I don't know. What is a product, Jaden?
So that's when you're multiplying something together and that gives you like the answer,
Oh,
right?
like
Yeah.
2
Okay.
times 2?
Yeah, that the product of that would be 4. Does that make
Oh,
sense?
yeah. I think so.
Okay. Good. Whew.
Whew.
Glad we figured that out. But now, like you said, this is crazy writing. What does that mean? Well, since you guys are all students of ours, you should know that the d over dx, that means we're doing the derivative. And it's saying we're taking the derivative of f of x times g of x. So in certain situations, it might be easier to just multiply those together first and then take the derivative. But in certain situations, it's going to be easier to do the product rule. It makes it just a little bit easier with the math. Okay. Um, so this says that we first take the derivative of the first function, multiply it by the second function. Then we add the first function multiplied by the derivative of the second function. So that's what the little apostrophes things mean. That's the derivative, right? F prime of x, that's what that would be called. And that is the derivative. And then g of x. Here, let's get a laser out so we can see where I'm talking about. So that apostrophe right there, that means that's the first derivative of our f function. Okay. And
Okay.
then same thing with g prime of x. That's what we call it. G prime, f prime. Um, that just says first derivative of x multiplied by g of x, and plus the f of x times the derivative of the second function.
Cool.
So we have two functions down here. Let's try this out with they're pretty easy functions. We probably could have just multiplied them together and taken the derivative. But this way we can just show it and we'll get the answer.
You think?
So, following our equation here, we need to take the derivative of f of x.
Okay.
So let's write that kind of underneath. So f prime of x, that's going to equal 2x. We just used the power rule, right? Where we multiply the exponent times the coefficient and subtract 1 from the exponent.
Cool.
Okay, that's what we get. F prime of x equals 2x. And then let's do g prime of x also. I'll do it here on the side. Woo, g prime of x. That equals 3 times 2
6.
x. Oh, good. I'm glad you answered that question.
6, Jaden, 6.
So this 6x squared, right? Because then we subtract one exponent. Okay. Now that we have those, let's kind of just plug all 4 of these into our equation and see what it looks like. So our first f prime of x, that was a 2x, and we're multiplying it, so I'm going to use parentheses to represent the multiplication. And then g of x, that is just a 2x cubed. Okay, not too bad so far, right?
No.
And plus f of x, we have an x squared, and then multiply it by g prime of x, that is a 6x squared. Okay, and now we multiply our functions together, right? Just our terms together. We get a 4, that's a 4. X is a 4.
Jaden, it looks like you were going to write a 2.
Dude, I tricked everybody, didn't I?
Yeah.
Okay, plus 6x to the 4th.
Nice.
And now I can add those together because they do have the same exponent. And that becomes a 10x to the 4th. Woo! So that is the derivative of these two functions.
Cool, dude. That is solved.
Yeah.
And it's
So,
probably a little bit mathematical.
Yeah. People might ask the question, what is this useful for in real life? And my answer is the exact same reason that all derivatives are useful, right? We can find these maximums, these minimums of projectile motion. We can find tangent lines to all of these motion diagrams that we can do. Does that kind of make sense? And then in really high math and physics, you'll see things called partial derivatives, and it is very useful in things like that.
Yeah. And I think that, when you've got this going on, Jaden, it's important to remember, right, that this derivative, you could take the derivative of this, like you said, of maybe displacement and get a velocity, right? We've just been working with super simple power rule situations, but sometimes you have more complex situations, and this is just another rule for taking derivatives to make life easier, right? So you don't have to. Anyways,
Yeah.
it makes it easier. And so if you have some big crazy equation, you can use different rules for the derivatives to make it make sense.
Yeah. And just remember, without all these cool rules, we would be taking it from the definition, and that was with the limit stuff, and it would just get a lot more complicated. Sure, we could do it, but who wants to when there's these shorter methods, right?
Right. So,
All right.
Jane, do you have another rule for us? I mean, first off, if there are any questions on this, please let us know.
Yeah. But Kip, I do have another rule.
Dude, you do?
And what goes along with multiplication.
Dude, maybe the inverse of multiplication?
Yeah, and that is
Division.
division. So we have our next rule is the quotient rule for derivatives. And like we said, that is dividing. So what happens when you have to take a derivative of two functions that are being divided by one another? Well, luckily for us, we have this other rule, and it looks complicated,
We got
kind
a
of.
comment saying that if do you even like math? Because if you did, I feel like you wouldn't love shortcuts so much. So, Jaden,
I don't know how to respond to that. I'm just ignoring it, I guess.
if you love racing, you still love shortcuts because they get you there faster.
Yeah, like in Mario
Yeah,
Kart,
exactly. Does think in
everybody
Mario
loves a
Kart
little
too.
short because you win.
Yeah, I'm thinking of like
Yeah,
Mario Kart 64 when you got to go through the waterfall. But I don't know if you know what I'm talking about. But
yeah. I saw this video of a person that just knows all the shortcuts on the new Mario Kart.
yeah,
They're on Rainbow Bridge. They drive off the edge, land on the course underneath it, and just are like miles ahead. And we're like, whoa,
yeah. So that's
that's
why
pretty
we
cool.
like shortcuts. So take that.
Okay, but anyways, we have this new rule, the quotient rule. Um, so we still have those little prime thingies, right? But this time it says that we take the denominator of the fraction, so g of x, multiplied by the derivative of the numerator, which is f of x, minus the numerator, so the top, f of x, times the derivative of the bottom, the denominator, and that is g of x. And all of that is being divided by the denominator squared. Woo!
Woo. Or an easier way to say it, Jaden, is low d high minus high d low over low squared.
Whoa, low
D
d
high
high minus high d low over low
squared.
squared. I get it. So high is the f of x, low is the g of x. D stands for derivative.
Yeah.
Okay, I got that.
You got that? You
Cool.
catch my drift? You picking up what I'm
Yeah,
laying down?
yeah. So, anyways, let's use those same functions from the previous slide. So I think we had f of x equals, was it x
Two.
squared,
Yeah.
and then g of x
G of x
was
was
equal to,
2x cubed.
okay, and then f prime would be 2x, and g prime woo, of x was 6x squared, right?
Yeah.
So let's put this into this wonderful formula. We get a 2x cubed that's multiplied by 2x minus x squared multiplied by the derivative of the bottom, which is a 6x squared. And that's all going to be over this 2x cubed squared.
Nice.
Whoa. Um, let's just dive into it.
Okay.
This is exciting.
This is so exciting.
Okay, so our top becomes a 4x to the fourth minus 6x to the fourth. I'm running out of room. I'm going to do a slash like this because I ran out of room. And that's going to be a 4 the sixth. Is my math good so far, Kip?
Dude, I think so.
Sweet. Oh, look at that. What a coincidence. Our top has the same degree, so we can add and subtract them. That's wonderful. So we get a negative 2x to the fourth divided
Jaden, I feel
by
like you may have done that on purpose.
x to the sixth. Uh, I think no matter what, they're always going to be like that, isn't it?
No, because if you had like, oh yeah, I guess.
Oh, well, I guess polynomials,
Yeah,
yeah, it would be a little bit more
that's
difficult.
true.
We would just have a lot more terms to add and subtract
Yeah.
together. But yeah, this is pretty good. Pretty good. Oh, cool. And when you divide with variables, you can just kind of cross them out, right?
Yeah.
So that's gone. That's gone. That becomes a 2 now, right? You kind of just subtract them off.
Yep.
And then what is a negative 2 divided by 4, Kip?
Dude, that's a negative 1/2.
So all of this equals negative 1/2 x squared.
Wow. Jin, you did so good. Now that is solved. Ba-jing!
Sweet. Ding! Not too shabby.
Not too shabby, dude. You're killing it. Killing it with those
Okay.
derivatives. Okay.
So this is exciting stuff.
So exciting.
Are there any questions on this stuff? These two rules. We have the product rule and the quotient rule. And like we said before, it's just helpful to understand and manipulate these functions so it's a little bit easier to take the derivative.
Yeah, so let us know if you have questions. We just wanted to give you guys some more tools for derivatives out there in your life. So if no more questions, we're going to move on to another section of some fancy dancy physics. No, Kelsey, I'm not using your beautiful pop filter.
What?
All right. So, Jaden, Newton's first law. So, many of you out there have probably heard of Newton's 3 laws, right? And
Was
people.
Newton really into politics?
Yeah, dude.
Why was he making laws, dude?
Dude, he was, right up there with the Queen of England. I think it was a queen at the time. It may have been a king. I'm not sure. But whatever. He was there making all the laws with them.
Okay. That's pretty cool.
No, Jaden. These laws are a little different. These are laws of the universe. So there's like a distinction between theory and law, right? So a theory is something that they haven't 100% proven, right? There's still some aspect of it that isn't necessarily true, or they haven't been able to prove that it's true. So say, for example, the theory of relativity, right? It's not necessarily the law of relativity because there's still some aspects that they can't get to fit in perfectly with it. But these are Newton's laws. So, Newton's kind of prideful calling them his laws. I don't know if he's the one that called them his laws. But he didn't actually make these laws up, right? He discovered aspects of the universe that are true. These are laws that already exist that humans have been bounded by. The universe has always been bounded by.
Okay.
So, no matter what happens, these aren't going to change. Now, with that, there is the first law, okay, which says that an object with a constant velocity will stay at a constant velocity unless there is a net force acting on that object. Okay? And for many of you people out there, I feel like Newton's laws have been taken and used in many instances besides just purely physics, right? So a lot of you guys have probably heard, an object at rest tends to stay at rest, and an object motion tends to stay in motion, right? But then there's
Yeah.
that last little aspect that says unless a force acts upon it. And so what that means, I was told that growing up, like, oh, well, it's harder for you. They'd always say you just need to get moving because once you get moving, right, then it's easier. And so that's like applying Newton's laws into your own life, even though it doesn't exactly work that way, but it's
Yeah. Yeah.
um but what it does mean is that if you have something that's just floating, let's say we're in outer space, because outer space is like the most
Ooh, I
easy,
like that.
yeah,
Yeah.
is the most easy spot to picture things, right? So you've got something that's floating out in space and it's not moving, okay? And no other force is acting upon it. It's just simply out there, Jaden. What's going to happen to that object? Is it going to move or not move?
It's not going to move
Exactly.
because, yeah.
So it's not moving, right? It has at that point its velocity is 0, right? And what we remember from weeks before, that acceleration is the change in velocity, okay? So if there's not something causing
Okay.
it to change its velocity, then it's not going to move. And the same thing is true with an object that is moving at a certain velocity. It will not change that velocity unless a force acts on it, right? Something's got to change it somehow. Okay?
Okay.
But Jaden, I've been saying the word.
You've been saying the word, yes.
Yeah, force a
Force, is that
lot.
the one?
Yeah, right?
Yeah.
But Jaden, what on earth is force? So I've been saying it.
I'm I'm glad you asked, Kip. Uh, so who remembers our second review question?
Ooh, was a or was the thought provoking question? Or no, wait. Oh yeah,
Well,
vector.
I guess
Yeah,
it relates to both
it
of those, huh?
relates to both of them. So yeah, our second review question, which was I remember now. Do you remember?
What is a vector?
Yeah.
Yeah.
What is a vector?
So force, it happens to be a vector, right? It has a direction and a magnitude, right? Uh, all forces are in directions, right? If you push something, it's going to go the direction you push it, unless there's other forces acting that make it go a different direction. Um, and then the magnitude is the actual number that you force into it. So that would be in newtons. That's how we would like to measure it, anyways. Newtons are good.
Newtons are good. Um,
Yeah.
yeah. So it's got a magnitude, right? And it's got a direction associated with it. So it's a vector, okay? And from Newton's first law, he states that the force changes the motion of it, right? So there's got to be some sort of change in velocity associated with it, okay? To help change its direction. So it's somehow going to be related to acceleration, right? Because the acceleration changes the velocity. Okay? And
Okay.
so with that comes the second part, which is the mass of the object, right? So the bigger the object, or the more mass an object has, there's a force, the force is related to that, okay? So Newton
Okay.
simply put it, the force equals the mass times the acceleration.
Okay.
So why is that matter? Why is like what is that? Right? And so this is where me and Jaden, right? Me and you were talking about this earlier today. We started questioning ourselves a little bit here because this is something that you learn in introductory physics and you just go, yeah, okay, force equals mass times acceleration. and you move on,
Yeah.
and you're done. But the thing is it's like, well, what is it? Well, we know it's a change in velocity, right? Change in motion of the object. But then there's that term mass out front. And so you have this mass times acceleration. So that's why we ask the thought provoking question, what is mass? Because
Right.
even if you're out in space and you have an object that's sitting still, right? Let's say that I have a little tiny, I don't know, I've got a baseball out in space
Uh,
and I put a force onto that ball, then that ball is going to move through space as I'm pushing it, right? It's going to have an acceleration
right.
associated with it. Well, if I have, say, a bowling ball, which is much greater, has a much greater mass, I'm going to have to add more force to that to get it to accelerate at the same rate as the baseball. Even though it's in space, even though there's nothing else acting on it, it's still going to take more force to get it going. And so, one definition of mass, even though we don't know exactly what mass is kind of its instantaneous resistance to movement almost, right? Like
Yeah.
it's the resistance to wanting to move. And so the bigger the object, and we're all aware of this, we've all tried to push big heavy things around, and we know how much harder it is to push that around
Yeah.
than to push around something that's smaller, right?
Right.
Even if you're like ice skating, right? If you try to push something heavy on ice where there's very little friction, it's still much harder to push it than something smaller.
Right.
And so that's where force comes into play. Um, and we're just going to take it at that face value and remember that force equals the mass times acceleration. And hopefully, with time, it will kind of start to sink in a little bit more. And there's an important
Yes.
part about this force times acceleration. In the last slide, I said that an object will stay at rest or stay in motion, right? Unless an outside force is acted upon it. But I also said the word net force. So, what on earth does a net force mean? Well, net means it's the sum of all the forces, right? So, you add up
Right.
all the forces together, and if that does not equal zero, then there is a force acting, or then you are going to change your acceleration, right? One of the most classic examples of this is, say you're standing on the ground, right?
Uh-huh.
Um, you're not moving through the floor, right? But the force of gravity is acting upon you.
Yeah.
And so, but there's also the floor is pushing back up on you. And so the net force on your body is actually zero. And that's why you're not just like falling through the floor.
So is that why there's not ever really cool parties in the core of the Earth, Kip?
Sure, Jaden. That's why we're all not just stuck there.
Yeah. Okay. That's pretty cool.
Okay. So, anyways, that part about normal forces is actually going to segue us into Newton's third and final law of motion. Well, I'm not sure if there's more actually, but I'm going to. The three most
It's
important
been
ones.
laws, right?
All right, Jaden, here we go. Third law of motion that has to do with force. There is an equal and opposite reaction. So, what on earth does that mean? Well,
Oh, we had
yeah, we had a
a
comment.
common
Yes, Newton's three
twist.
laws. Thank you, Ian of Flat Fac Faceo. Sure. Yeah, that's what we're doing. We're going through Newton's
Yeah.
three laws. So we are on to equal and opposite reactions. Here we go. So Jaden, this is also one of those things that people tend to use not just inside of a physics context, right? So people will kind of talk about it similar to karma, right? Like you give something out, you get something back. Um, and so there's this equal and opposite exchange. But it's proven as a law in physics, it actually exists and is there for real. So Jaden, what does this mean? Well, like I said in the last slide, if you're standing, this is the sure, not exactly Kelsey, but it's close. Um, FMA, uh, it's alchemy. You know, you got your
Full
equivalent
metal alchemist,
exchange.
right?
It's somewhat similar, but
that's
that's more of like
that's more like
conservation.
conservation of energy.
Yeah, that's what I was
Oh
gonna say,
yeah,
dude. Nice, so smart.
dude, we're just vibing right now.
On the same wavelength, dude. Um, cool, cool. Okay, so we've got equal and opposite reactions. So something in the case of us standing on the floor, right? We're standing on the floor with a force because of our mass in our body, and then that floor is actually pushing back up on us with the same force. Support
Here we
forces. Can you clarify what that is meaning? I'm not sure what you mean by support forces. Um, but
go. Are you?
that was from the
I don't
comment.
know. We might kind of get into that more
Yeah.
in the next slide. And
I was wondering that was what you were referring to with the floor pushing back up. So that is a normal force, right? So that's anytime the floor or whatever you're standing on is pushing back on you, it's going to be pushing back with a vector that is equal in magnitude in an opposite direction to the same as what you're doing, or the same force that you're acting on. So if we've, but thank you for your question. I really appreciate it. Keep asking away. Um,
yes,
please do. Okay. So, anyways, you've got force pushing down, right? You're standing on the ground, and then you got a force pushing back up. They're equal and opposite. Jaden, another equal and opposite reaction is, let's say I was to punch you in the face because I'm real mad at Jaden. He's been a jerk.
dude, I would be like, "Ow! Hit my face!"
Dude, I'd be like, ow, Jaden, why did you hit my hand?
I would be like, "What are you talking about, dude?
No, dude.
You hit my face."
No, dude, I'd say you hit my hand.
And why would you say that, Kip?
Well, Jaden, do you remember reference frames?
Yes, I do.
So,
There, in that situation, you would be saying, in your reference frame, my face hit your fist.
that's what I'm saying.
You're a little jerk, dude.
And so, because of that,
That's
right?
what I'd be.
Because the reference frame, I'm saying my hand is standing still and your face is
Oh,
accelerating towards my hand, right?
okay.
And so,
And Newton's third law is saying that we both felt the same force
exactly.
on your hand and on my face.
Yep.
Uh,
So what does that have to do with I mean, so Jaden, does that mean that it's possible to actually ever win a fight? Because if you're always exchanging an equal force, then
well, think about it this way. Think about you driving on the freeway and uh, you know how sometimes you get bug splats on your windshield.
yeah.
Who won the fight? Both of those felt the same force, right? Our windshield and the bug, but I'm just saying, who won the fight?
True that. Um, so yeah, that's a good way to think of it. But yeah, this is a law, right? So no matter what, um, just out of curiosity, when did you guys start streaming? So are you talking about right like tonight? As of tonight, we started about 45 minutes ago. Um, actually start streaming. I don't know. We've been doing this for several months, but relatively new to
Yeah.
Twitch. Mainly been doing it on YouTube. So there you go. That answers both those questions for you.
Yeah, and tell your friends
Yeah.
if you're liking this stuff.
Yeah, and every Thursday night we do, homework help as well. So send questions and we answer them. But okay, back to Newton's laws. Um let's move on to, well, I guess we're kind of done wrapping up with Newton's laws here. And now we're going to move on to some free body diagrams, Jaden.
What does that mean?
Dude, I don't know. Dude, that body's free. It's not a prisoner anymore. It's good to go.
Yeah, I'd say.
Um
So I see you have this rectangle and these arrows. I'm guessing that's what the free body diagram is, but can you elaborate on that?
nah, I'm good for tonight. Yeah, I'll go ahead and
Yeah,
elaborate. I'm done. I'm taking off. No, okay, so a free body diagram is used to show forces, right? So if you remember, we've been talking about net forces. So in lots of cases, lots of instances, you can have a force, you can have multiple forces acting on an object. The example of you standing on the floor with gravity, right? That's that's an example. Gravity pulling you down, and the normal force pushing you back up. Another example of this would be, say you're say you're walking, right? You've got friction forces, or if you're in a car, right, your tire has a friction force, but you also have a force pulling you forward. So this is kind of a way just to kind of keep your mind wrapped around what's going on, right? It's a way to keep track of what's happening.
Okay.
Um, and
So
yeah,
this free body diagram, you can put all these different forces in it to tell you which direction they're acting on and see kind of what, I guess, in certain situations kind of cancel each other out or act with each other or against each other. Is that kind of what you're saying?
that is exactly what I'm saying. So it's a way, right, when you get in a really complicated situation, you draw these out so you can keep track in your mind of where everything is. Um, and so you draw these forces, right, because they have a magnitude and a direction.
Right.
You draw the arrows based on the direction that they're facing. Yes, this is how you kind of
Yeah,
start. That's exactly right. You kind of do this
that is
to,
a good question.
yeah, that's a great question. You do this to kind of start figuring out, you know, what vector is or what force is acting on it in which direction, and then you can kind of figure out how to sum them together and sum the different components together. So, anyway, so you've got the angle, right, and then you've got the magnitude, and you represent the magnitude based on the length of the line. So if you've got a stronger force, um, sorry, the question for you watching on YouTube is this where you start to use vectors to find where the net force is going to go? Um, and so yeah, I'm gonna go ahead and we're actually gonna talk about that a little bit more. But anyway, so you've got these forces acting in different directions, right? You draw them out.
Uh-huh.
And Jaden, the nice part is because we're physicists and not artists, we go ahead and um, just make it a box every time. It doesn't matter if it's a cow, an elephant, a car, a Jaden, a Kip. Who cares? It doesn't matter. You just
Yeah.
always draw a
It,
box.
it's simple objects.
Yeah. So let's go ahead and I'm gonna go and let's hop on over to the Jamboard and draw some stuff out, shall we?
Yeah.
Let's talk
Uh,
about why this is important a little bit. Okay, so Jaden, we've got these two forces acting on it, right? So we can go ahead and we can write if we want to find the net force, which is the sum of forces, right? You do the sum of F. For all you guys that remember when we talked about integrals, that squiggly E thing means summation. So we have the sum of F is equal to, and then we can say F2 plus F1. Wow! And you're summing our forces
Whoa.
together, okay?
Okay.
So normally what we like to do is we'll take the horizontal here, okay? Boop. And we'll make our angle off that horizontal. So you've got a theta 2 here, and then sure, we'll put a theta here. Theta 2 there, or 1, I guess. Like that. Okay.
Yeah. Okay. And theta just represents angle.
Yeah.
Okay.
So that is a good question. It's just out of curiosity. Is there a trick to knowing the divergence tests to use for an infinite series, alternating series test, absolute series test, ratio test? We're not going to go over that tonight, but if you want to hop back on Thursday night, we can.
That's
do
a really
that.
good question, though.
Yeah, that is a good question.
Are you, out of curiosity on my end, are you in Calculus 2 right now? Because if you are, we would love to help answer any questions you have for homework on Thursday nights.
Yeah.
But yeah.
AP Calculus BC, essentially Calc 2. So yeah.
Okay.
Cool. Yeah, so if you want to hop on Thursday nights, we'd love to help you out. Okay. So
Well, I love the questions.
Yeah, thank you for asking them. We appreciate it. Okay, so anyways, Jaden, back to this really quickly.
Yeah.
So Jaden, when we sum two vectors together, right, we can create essentially a third vector. So just really quickly, I'm going to draw in where the net force is approximately going to be, right? So we've got this vector that's pulling down this way, right? And we have one pulling up. But the magnitude of this one looks pretty big. So it's probably going to be, somewhere in between the two of these, probably below, right? And so our net force is probably going to be somewhere like that, right? Would you agree with that?
I do agree with that.
So
it might be a little higher, but
yeah, but that's somewhere in there. And so because it's right in there, we can go ahead, and that is actually going to be the direction in which this force is going to be moving, right? Because what's essentially happening is it's like if you have a t-shirt or something and it's getting pulled in different directions, ultimately one way, I don't know, if you're fighting over something, right? Whatever force wins, that's the way it's going to get pulled. And so if you've got things pulling on it in different ways, there's going to be ultimately one way that it's going to go. And it's going to be kind of like in between the forces that are acting on it.
Dude, and then I would say, hey, man, you're stretching my t-shirt.
Back off. Say that's what you get for punching my hand with your face.
With your face. Yeah. Okay. So let's do those vector components, and should we do that with
So I guess the first thing we can just really quickly about showing adding vectors together, right, is you have an x and a y component, and you can just simply add those two together to get the new vector. So if you had something just really quickly, if you said like f2 equaled I don't know, say like 1 comma 2, right? And that's your x and y component, and this was like I guess there wouldn't be an x component, would there?
Yeah, that would be
0,
0, 2.
comma 2. Um, and then this next one would have to be, because we're in the fourth quadrant, and maybe we should talk about quadrants sometimes. But we'd have a negative, say, 2 and a negative 3.
That would be -2, negative. Yep.
Yeah. So then you would add those together, right? And you just add your x's and your y's together. And so you would get a -2, comma, -1. Boop. Just like that.
Yep. That would be your direction and magnitude right there.
Yes, it would. So that would be this blue
With
line right here that we drew. Okay. So that's where it's going to be being pulled to. But normally in physics, we don't care so much about that, right? What we actually care about is breaking it up just like we did for velocity, and with these projectile motions we want to break it up into our x and y component. And so you can do, so like sum of forces in the y equals f of 1y plus f of 2y, and sum of forces in the
the
x direction
X.
equals f of 1x plus f2x. And you remember
Right.
you do this by taking cosines and sines of the force and that angle that we know, right?
Right. Yep.
And so a lot of times what you'll see in physics questions is you'll see something that will ask how much force needs what's the net force on this object in order to accelerate it, right? At this rate. Or another question you may see, yes, we are. Well, I am. Jaden has a mouse.
I have a mouse computer. Question was, are you guys using a drawing tablet?
Yeah, I think I'm going to go ahead and throw up our chat onto our live stream so everyone can just see, because that way everyone can become friends.
It can be, yeah,
Best buds. Okay.
below our faces. That'd be pretty cool right there.
Yeah. Um.
Sure.
Anyways, so we can, based on your angle, normally in physics, you can say that not always, this is not always, but f of y normally equals f sine of theta, and f of x equals f cosine of theta. As long as you're taking it from the horizontal, right?
Right.
So there you go. That is mathematical, and we have, I believe, finished everything for tonight.
Yeah, that was exciting.
Woo! So yeah, thank you guys all again for watching. Here, Jane, I'm gonna show our T-shirt just one more time, because even though it's not all the way up yet, but it's so cool, While we finish up our
Yeah,
discussion for tonight. Um,
I did. It's pretty cool.
okay, so alrighty. So for all you guys, recap of what we talked about tonight. We talked about derivatives using the product rule,
Product and
and
quotient.
thank you for saying well done. I appreciate it. We talked about the product and quotient rule for derivatives, and then we also went ahead and talked about Newton's three laws tonight. Jaden, we didn't
Yeah.
come up with a plan for next week, did we?
Um, I think it would make sense to maybe do a little bit more with the force diagrams, and then after forces, what do we get?
I don't know. Maybe we'll go all the way to momentum, but who knows?
Yeah, I don't know.
So
We can get some more. derivatives or integration rules in.
Yeah. And you are right. 3 blue, 1 brown does have a lot of good content and regarding calculus as well. So those who are interested, he does have a lot of good extra resources out there to watch as well. Oh, the Box Mountains put a smiley face. So,
Hey,
hey,
the Box Mountain
the
is
Box
on.
Mountain has
Yes.
been quiet for a long time. So, thanks for joining. Cool. Alrighty. So that is going to finish us up for tonight. And don't forget Thursday nights at 8 p.m. Mountain Standard Time. I'm not sure what that is for anyone else out there. But we do homework questions, so go ahead and you can send them to our email, which is just after.math.livestream@gmail.com. And you can send us
Live dot stream.
live dot stream. Whoops, thanks.
We have a lot of dots in there.
dot 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 dot. And you can send us all your questions. Thank you, because he said, of course, you guys are kicking butt. I think he just got on. That's personally what I believe, but we have not set up a Discord yet, and I am not super familiar with Discord, and I probably should be.
That's a good.
That
That's a good
that
idea,
is a
though.
good idea. We should do that. Jen, do you know Discord? Because I don't.
I
You use it for your League of Legends?
I've sometimes used it. Yeah. I haven't been the one to like create any of the. I don't even know what they're called on Discord, so maybe.
Cool. Well, thank you for that.
Okay,
Yeah,
so
we'll look into Discord this week and add it on. Maybe we'll get there. We're slowly learning everything, but thank you for that. I appreciate the recommendation. So yeah, we will on Thursday nights we go over homework. So if you send it to us before we go live, then it's that much
we
easier.
can have a
We can have it
little
set
bit
up.
better
Yeah.
answer.
Cuz if I mean we're pretty good at math, but sometimes we're not perfect, so
What was that?
cool. Well, thank you and we appreciate all those watching tonight. And good night.
Yeah. Yeah. See you Thursday,
See ya.
maybe.